Okay, now that we have learned perturbation theory, we'll start applying it to some standard problems, some problems that are traditional in learning quantum mechanics, mainly analyzing the hydrogen atom with better and better amount of accuracy. Okay, so the first problem that I am going to discuss is going to be the effect of the electric field on the hydrogen atom. Okay, so this is called the Stark effect. What you do is you apply electric field to the system. Okay, we looked at this in idealized conditions like particle in a box and such things. Now we are going to look at what happens in hydrogen. Okay, so this is the effect of an electric field. Okay, so suppose I have some electric field in the z direction. So let me just assume it has some magnitude E and Z. So it corresponds to a potential which is going to be V equal to minus E, okay, minus E. Okay, so the potential is the potential energy, the potential energy of the electron is going to be E times minus E times Z. Okay, so we are going to get some E times Z. And since we are working in spherical coordinates, we'll write this as E times R cosine theta. Okay, so that is the potential energy that we are going to add to the system. Now, as soon as you do that, okay, so if you just try to plot this potential in the z direction, you have this Coulomb potential near the origin, and on top of that, I'm adding a linear potential, which, okay, in principle goes from minus infinity to plus infinity. So what happens is that this overall potential gets deformed into something which looks like that. Okay, so you can say that, well, this is not really a small perturbation because eventually my energy will be above that of the energy at infinity, okay, which would mean that this is not a bound state anymore. Okay, but what we are going to assume is that the electric field is not really so large that it's not going to break the hydrogen atom apart. Okay, obviously you can apply such a large field that you can just take this electron out of this place. Okay, so those types of fields are also useful for analyzing materials, atoms, etc. So this year's Nobel Prize, if you look at the physics behind it, they are these attosecond, extremely fast laser pulses which generate very large electric fields for very short periods of time, which results in the deformation of the orbitals and ionization and such things, and so gives you information about the structure of the energy states. Okay, so it's an important case, but here we are going to assume that this electric field is sufficiently small so that the wave function here is perturbed just a little bit, resulting in some polarization, so that we are going to look at the energy. Okay, so we are going to look at the effect of this. So this is, although it's V, okay, what we are going to do is we are going to say this is our H1. Okay, so this is the perturbing potential that I add to the hydrogen atom. Okay, so what do we do? Well, we have these energy states, and they are, a lot of them are degenerate. Okay, so since this is the electric field, it doesn't couple to the spin, so we don't have to worry about the spin degree of freedom. But in any case, I have this energy level E100, which is the ground state. So if I just ignore spin, we can treat it as a non-degenerate. Okay, so I'm not going to worry about spin. But the next level is made up of these E2 states. So I have E200, okay, and LM. I also have E210, E211, and E2 minus 1. So these things all have the same energy. So this next energy level is fourfold degenerate. Okay, so this is when I don't have any H1. Okay, so when H1 is equal to 0. Okay, then the electric field is 0. Now when I apply the electric field, we'll see what happens. Okay, so for the ground state, I need to, okay, I can use non-degenerate perturbation theory. So it's going to be just the expectation value of the system between the 1, 0, 0 states, right? So this is going to give me the 1, 0, 0 energy shift to first order, right? Okay, so the structure of all of these expectation values are going to involve the radial and the angular parts of the wave function. Okay, so whenever I have something like okay, some n, I'll stay within the same n, and I'll have an L and an M, and then I have an H1 here, and then same n, in this case just 0, that's 1 or 2, and then L prime, M prime. What does that correspond to? Well, that corresponds to first a radial integral, right, from 0 to infinity. The radial function NL, okay, complex conjugate, but remember these are all real, okay, and L of R, and then I have R and L prime of R, and then I have this H1, which in this case our radial part, let me clump the constants to that also, ER. Okay, so this is my H1, the radial part of H1. And then I am going to need to do the, okay, R squared dr integral, right? And then there's also this angular part. The angular part now contains these LMs, so I am going to get YLM, right, complex conjugate, function of theta and phi, and YL prime M prime, again function of theta and phi, and I have the cosine theta, which comes from my H1. Okay, so these things in parentheses are the H1 contributions. And then I have the angular integral, okay, sine theta d theta d phi. Okay, so that will be the form of this inner product. Okay, first of all, just very simply looking at this, you can see that there's no phi dependence in H. Since there's no phi dependence in H, because of the orthogonality here, I must have m equal to m prime. Okay, so if I have a different m's and m primes, I'm always going to get 0. Okay, so this is this piece here is proportional to delta m prime. Okay, so in this basic case, I have those things satisfied. But let's now look at, okay, so let me just save this, keep this. But I'm going to look at, it's more economical to look at the, basically the angular part first. Okay, so this is going to have, okay, so if I just look at the angular part, you see 0, 0, 0, 0, okay? So it is integral of y 0, 0, okay? I'm going to put the m index below because sometimes I put the complex conjugate here and the notation gets cluttered. Okay, so I have these y 0, 0s. Now y 0, 0 is the simplest, okay, spherical harmonic that you can have. Why? Because it has no angular, okay, dependence. Because it has no angular dependence, the only thing it contains is a normalization constant. Okay, so you integrate this over all angles. If you integrate this over all angles give you 4 pi. So this thing must be equal to 4 pi. So these things are just 1 over square root of 4 pi's. Okay, so that's all there is to it. The y 0, 0 object, right? So your product gives you 1 over 4 pi. When you integrate it over 4 pi, you get 1. Okay, so that's very simple. But then now I have the rest of my integral here, which says I have a cosine theta, sine theta, d theta, d phi. The d phi integral will always give us 2 pi for this problem because there's no phi dependence. Okay, so since there's no phi dependence, this always, okay, in fact, let me just put it over here. This is, for our problem, always gives us 2 pi, okay, and you integrate over all phi angles. All right, so I have something like this. So looking at the theta integral, I have a sine theta d theta here, which I can take as d cosine theta, okay, with a minus sign, okay, but remember that this theta integral can be transformed into a dx integral, okay, so if you just consider this as dx now, the new variable is cosine theta, okay, then you can just write this integral as being proportional to the dx integral of x, okay, so cosine theta will just become x dx minus 1 to 1, okay. So whenever you have this sine theta d theta structure, you can just replace that with minus d cosine theta, but this minus sign goes away because you interchange the limits also. So you get very nicely an integral from minus 1 to 1 with cosine theta equal to x, and I have another x here. Okay, so that's that, and it's an odd function, so that's 0.
I have a question.
Yes.
Why do you have 2 dx's?
Why do I have 2 dx's? Because, okay, it looks better that way, I guess. Okay, so I have something like that, which gives me 0. Okay, so this object here is 0. Okay, this is not really too surprising. We discussed that these things have spherical symmetry, and you apply, okay, something like z or x or whatever, you get 0 on the average. Yes.
I couldn't understand when over square root of 4 pi thing.
Okay, so these are just a set of functions, okay, the spherical harmonics, and y0, 0 is the simplest spherical harmonic which contains no theta or phi dependence. It's just a constant, okay? So it's a constant, which means that it has to be normalized to 1, okay? So normalization to 1 forces you, okay, so this y0, in fact, any y Lm, okay, star y Lm, okay, integrated over all angles, meaning sine theta, theta, and d phi, has to be equal to 1. So for the y0, 0 case, just, okay, this is 4 pi. Okay, other questions? Yes?
For the curvature delta we found in the angular part, isn't the orthonormality applicable for the sin theta integral only? We have an extra cosine term.
No, this m part is separate, okay? The m part, the phi part, so these YLMs are, okay, so the YLM of theta and phi looks like, okay, some constant, okay, because these PLMs are not normalized, okay? And then I have an e to the I m phi term here, okay? So the if you have different m's, if you have two different YLMs like this, okay, which are being multiplied together, what you are going to get, okay, so this YLM complex conjugate YL prime M prime is going to be something, okay, some function of theta and constants, etc. And then I'm going to get an e to the I, okay, M prime minus M phi like this. So that's the only phi dependence in this, okay? And this is going to give you 0 unless m is equal to m, unless m is equal to m prime, okay? So it's independent of the theta angle. Just looking at the dependence on phi, which is just trivially like that, you can say that m must be equal to m prime, otherwise you get 0. Okay, other questions? Okay, so we are now on our way. Let's look at this stuff over here. Okay, so this is now a degenerate set of states. So in order to find out what the first order shift in the energy is, we have to construct this matrix, okay, which is going to contain now all these other terms. So now I need inner products which look something like this. N equal to 2, and L can be something, okay? M can be something. Then I have this H1, and then again 2. L could be different, right? Because it can be 0 or 1. And then there will be some other M prime in general, but we just so that M must be equal to M prime, otherwise I'm going to get 0. Okay, so I need to construct this matrix now. So let me just use that sequence that I have over there. So on the right-hand side, I can have 2, 0, 0, 2, 1, 0, 2, 1, 1, 2, 1, minus 1. And okay, so that's the right-hand sides. On the left-hand side, I'll put in the same sequence, 2, 0, 0, 2, 1, 0, 2, 1, 1, and 2, 1, minus 1. Okay, so our first condition, which says that M must be equal to M prime, says that, for example, if this is 0, if this m is 0, then I have m prime equal to 1 or minus 1 is out. Okay? So if that is 0, then again, these two guys are going to be zeros because they have different m primes. Here, I have 2, 1, 1. So I could, in principle, have some value here, but I have 0 there, 0 there, and 0 there. Okay, and this is minus 1, so this has to be 0 all the way over here, except that I could have an element here, and then these things, of course, have m and m prime equal to 0, so I could get something out of that. Okay? So let's just start looking at that stuff. Let's look at these diagonal terms again. Okay, so I have this 2, 1 because they'll give me the same thing, right? The m parts are going to be orthogonal, and the we'll have to look at the other parts. Okay, so the question is, what is 2, 1, say 1, and then in the middle I have this h1 and 2, 1, 1. Okay, so I'll again look at the angular part first. Okay, so this says that I need to look at, okay, so let me write angular part. So I'm going to have this y 2, y 1, 1, right, Lm, y 1, 1, complex conjugate y 1, 1, times this cosine theta, sine theta, d theta, d phi. Okay, so now I know that this d phi is going to give me 2 pi, okay, because the m indices are the same. But I don't know about the theta part, so I have this nice table of, yes, spherical harmonics and hydrogenic wave functions. Every physicist has to carry one of these things, at least on their phones. Okay, let's see, y, and also you need glasses if you are my age. Let's see, y 1, 1 is something, okay, so this is given as 3 over 8 pi, and I have 2 of those, so it's actually square root, but then I square it, it's just this number, okay, coming from both of them. And then I have a sine theta coming from each one of these things, so I have sine theta and sine theta, all right? And then I have this cosine theta factor, and then sine theta d theta. Okay, so same type of arguments that we did last time. Okay, so let me just put the 2 pi from the phi integral over there, and this is a theta integral from 0 to pi. So what this becomes equal to is 3 over 8 pi times 2 pi. All right, this thing here I'll convert into a dx, okay? And then I have an x here and a sine squared x, which is 1 minus x squared. Okay, so you see it's a minus 1 to 1. So I have an even function here, an odd function there. So this is again equal to 0. Okay, just from the symmetry of these things. So very nice. This is 0. and that's 0, okay? Because independent of m, I'm going to get those. Okay, so let's look at other diagonal terms. So let's look at something like okay, let's look at that 2, 0, 0. 2, 0, 0, H1, 2, 0, 0. Okay, so again, I'm going to look at the angular part. And the angular part is going to be, okay, so the 2, 0, 0 is going to be, oh, this is easy, right? This is the y00 bit that we did already, because these are the LMs, y00, h1, d theta, sine theta, d theta, d phi, okay, that we just saw that that's equal to 0, okay? So for the 0, 0 case, I'm going to get 0. Well, actually, I did not do it, but okay. I thought I did it. Yeah, okay, but here it is, okay. We did it for 1, 0, 0 for the ground state. In any case, so this is 0. So let's look at 2, 1, 0. Okay, 2, 1, 0, H1, 2, 1, 0. Again, the angular part is going to be y1, 0, y1, 0, and then I have this cosine theta, which comes from the h1, and then I have sine theta d theta, and the factor 2 pi, which comes from the phi integrals. Now, y1, 0 is, okay, I'm just checking if I did this before because I have just such short-term memory. Let's, okay, so let's see what y1, 0 is. So y1, 0 squared has a 3 over 4 pi coming from these two guys, and then it's just cosine theta. Okay, cosine theta times cosine theta from these two terms. Then there's yet another cosine theta from h11 and sine theta d theta. Okay, so it's okay again 0. Why? Because this is the minus the x bit. This is x, and this is x squared. So the whole thing is just equal to integral minus 1 to 1 x cubed dx, right? So again, an odd function. Integrate over a symmetric integral will give you 0. Okay, so by this time you perhaps start to think everything is going to be 0, right? But we have these two nice faithful things which I left to the end, okay, which are okay, going to give us something. All right, so let's see what they are. So 2, 1, 0, 2, 1, 0, H1, 2, what? 2, 1, 0 and 2, 0, 0, right? So again, let's look at the angular part first. So this is now going to be y 1, 0 complex conjugate, y 0, 0, okay? And then I have this cosine theta and sine theta d theta, and the phi integral gives me 2 pi. Okay, so y1, 0, I have it over here, is square root of 3 over 4 pi. y0, 0, okay, we discussed this is the object which doesn't have any angular dependence, so it's 1 over 4 pi. So there's a cosine theta which comes from the y1, 0. Okay, y0, 0 doesn't contribute anything, so there's another cosine theta here. And then there is this sine theta d theta, okay, and the factor 2 pi. So same sort of things. This is going to give me square root of 3 over 4 pi. Okay, so this is minus dx, but there's a 2 pi comes from the phi integral. So I am left with x squared dx minus 1 to 1. Now I have an even function, which is going to give me something finite. So it's going to give me, what, 1 over 3 times 2, right? So this is going to be square root of 3 over 2 times 2 over 3, right? Please check my algebra. So it's going to be 1 over square root of 3. Okay, so that's the result of the angular integral. Now, what about the radial part? So the radial part is going to be, now I need the radial functions. Okay, so the radial part is going to look like R, okay, complex conjugate technically, but these are real, 2, 1, right? H1, and R2, 0, I have R squared dr, 0 to infinity. Okay, let's just put these things in. R21 is 1 over square root of 24. Okay, A, which is the bore length, bore radius, 3 over 2, R over A, e to the minus R over 2A. Okay, that's R21. Then I have this H1, which is E times R. And then R20, which is 1 over square root of 2, A to the minus 3 over 2 again. And then I have, where are we? 1 minus 1/2 R over A, e to the minus R over 2A, and we are not done. We need the R squared dr. Okay? So I need the integral, 0 to infinity. Okay, so let's see. This is equal to 1 over root 48, okay? And I have E times E, which I can take out of the integral. And then a bunch of R over A's, right? Now, you see these A's multiplied together give me 1 over A cubed, okay? So since I have these R over A's, I want to use them. So there's an R here without an R over A. But otherwise, I have 1, 2, 3, 4, right? 4 factors of R without an A. And I have an 1 over A cubed down here. So what that means is if I multiply this thing by A and divide by A, it's going to be 1 over R to the A all over the place, right? So I'm just multiplying by a and dividing by a. So I'll also change the integration variable. So I'm doing several things at once. I hope it will be clear. So what I am also saying that I'm going to change my variable r over a to u. Okay. So if I do that, I am dividing all of the r's here by a's. Okay, 3 of them come from that. 1 of them comes from an additional factor there. So what do I get? So this is 1u. So this is going to be u cubed, right? Please check my algebra. So 3 factors, no, u to the 4th, sorry. There are 4 r to the a, r over a's. So that's 1, that's 2, and that's 2 more, right? So this is 3 and 4, and that, okay, so that will be our du. Okay, and then I have 1 minus 1 over 2u e to the minus 1u, because these are r over 2a, so it will be just r over 1a. And that's it. Okay. So what's the integral of u to the 4 e to the minus u integrated? 4 factorial, right. Okay, so this is going to give me, okay, let me as well take care of this. This is, so 48 is what, 3 times 16, right? And I have E and A, and this stuff is unitless. Okay, I should get something with a length as I expect. Okay, so I'm going to get, okay, 4 factorial minus 1 over 2, 5 factorial. Okay, so there's a factor 4 here, so I can write this as E A over root 3. If I divide this by 4, I get 6 minus, let's see. So if I divide this by 4, it's 2 times 3 times 30, so it's 15, right? Okay, so this is 9. In any case, okay, so let's just write this minus 9 A over root 3. You see, it has units of energy. Okay, electric field charge times distance. But this is not, of course, the whole story, because there's a 1 over root 3 here, over there. So this object here, going all the way back here, is equal to the angular part, which is 1 over root 3, times the radial part, which is minus 9 A over root 3. So there's also a little bit more reduction, A. Okay, so that's our result. Okay, so going back to our matrix, we have found this element, but since this object is Hermitian, we have also found this one, actually. So it's going to be minus 3 E A and minus 3 E A.
Sir, how do you
Yes.
know it is Hermitian? Because it's a real measurement?
Okay, H1 is Hermitian. Okay, so since H1 is a Hermitian, we have this, okay. All right. So now again we have one of those cases where it's very nice in block diagonal form. So you see, if you take these, if you make these orders in some sort of different way, of course these things will go to other places. For example, you can have the order such that, okay, these things can go to this point and that point, okay? Then of course you are going to have bigger block diagonal matrices, but if you can rearrange these rows and columns so that you have a smaller block diagonal matrix in the whole matrix, okay, it's easier to identify the eigenvalues, right? So looking at this form, we can easily find out what the eigenvalues and the eigenvectors are. Okay, so the simpler eigenvectors correspond to these diagonal terms. Okay, so there's going to be a lambda equal to 0 case with an eigenvector 0, 0, 1, 0. Okay, there's another lambda equal to 0 object, which is going to be this thing, 0, 0, 0, 1. And then I have this bit here. Okay, so that matrix is again minus 3 E E A, okay, times this sigma x matrix. And because I know the eigenvalues and eigenvectors of the sigma x matrix, I can easily identify what those things are. Okay, there's going to be a +1 eigenvalue for this, which corresponds to a -3 eigenvalue. Okay, so the +1 eigenvalue of sigma x is going to be the -3 EEA eigenvalue of the bigger matrix. So I'm going to get lambda equal to -3 EEA with an eigenvector, okay, corresponding to those two rows and columns, which will be 1, 1. So I have to normalize it, so it's going to be 1 over square root of 2. And the other eigenvector is going to, okay, eigenvalue is going to be the -1 eigenvalue of sigma x. So it's going to be 3 EEA, and I'm going to get 1 minus 1, 0, 0, 1 over root 2. Okay, so what does this mean? Well, going back, all the way back to our problem, there are these eigenstates, okay, 4 eigenstates which have 4 equal energies. Now we see that, okay, there's 0 change in energy in 2 of those states, and some finite plus and minus change in energy when this electric field is finite. Okay, so the way, again, I represent this is that the 2 of these objects, in fact, I should not exaggerate it, okay, so it's a perturbation, so it's a small change. So 2 of these states will, okay, depart, but 2 of them will continue to have the same energy. So which ones have the same energy? Well, they are the ones which correspond to this 3rd and 4th column or row. So they are the 2, 1, 1 and 2, 1, minus 1 states. Okay? And the others, for example, the one which goes up in energy with lambda equal to 3, EA is 1, okay, so this state here is 1 over square root of 2, okay, 2, 0, 0, minus 2, 1, 0. And this one, which moves in the minus direction, is 1 over root 2, 2, 0, 0, plus 2, 1, 0. Okay. and this 1, 0, 0 state just doesn't change its energy. Okay, so this is the Stark effect. Okay, anything that has a magnetic eigenvalue, okay, anything that in which the LZ is not equal to 0 does not change its energy. Okay, I don't know if I said it correctly. Those LZ equal to plus or minus 1 states do not change in energy, but the LZ equal to 0 states shift in energy by this much. Okay, so the shift in the energy here is 3 times the electric field times the charge times the Bohr radius. Okay, so just looking at the this object, okay, so this says that if I were to take, okay, maybe I'll discuss it a little bit more in detail. So we have these new states now, and unlike the case of a non-degenerate case, okay, non-degenerate state under the effect of an electric field, these things shift in energy, okay? And our argument for example, the E100 state was that, okay, I have this state which is, okay, spherically symmetric near the origin, and I shift the position of the particle by applying an electric field, so the position shifts by a certain amount. Okay, so it shifts from the origin by a small amount, and the amount that it shifts, okay, is proportional to the electric field. So the dipole moment that is produced, the P that's produced, is proportional to the electric field. So the energy, which is proportional to P times E, is going to be proportional to E squared. So that's why we do not get any effect in first order perturbation theory. So what happened here which changed this? Well, apparently this linear combination of these two states like this must have some built-in original, okay, dipole moment associated with them. So let's just perhaps look at that very quickly. So if I now look at the state, so suppose my particle is in this new state which I constructed, which is going to be an eigenvector of this H1 matrix. So if I have my psi now equal to this object, okay, let's look at the one which goes up, 1 over root 2, 2, 0, 0, minus 2, 1, 0. And suppose now I want to look at the expectation value or the position of the particle in the z direction. How would I do that? Okay, I would just take psi, z psi, and that would just be all of this stuff, 1 over 2, 2, 0, 0, minus 2, 1, 0, the way around. Okay, z is r cosine theta, and then over here I have 2, 0, 0, and minus 2, 1, 0. But these are things that we have calculated already, right? So we have calculated these inner products already. The diagonal ones gave us 0. Only the cross terms were finite, and they were equal to, okay, so they were equal, so let me just remove this factor 1/2. It's going to be minus 2, 0, 0, r cosine theta, and to 1, 0. Okay, remember it's right over there, except that we had EE stuff in front. So this is just going to give us 3 times A. Okay, so even without any electric field, okay, even if there is no electric field, if I just look at this state, okay, that's just linear combination of 2 states of the system with the same energy, okay, 2 degenerate states. I make a linear combination of them, okay, the linear combination of L equal to 0 and L equal to 1. When the particle is in that state, it automatically has some shift, okay? The average value of Z is not at the center. So this linear combination is not spherically symmetric. So the electron in that state is a little off from the origin. So you have some natural dipole moment associated with that state. And now if you turn on an electric field, now you get an energy which is linear in the electric field because you already had some dipole moment associated with that case. Okay, so this non-symmetric combination of these orbitals, okay, so this is going to be obviously an excited state of hydrogen. The excited state of hydrogen has some natural dipole moment, okay, even if you do not apply an electric field, it is already a polarized atom. And then the electric field just corresponds to some energy. Okay, let's have our break.